Hi, so the purpose of this video is to get into the microscopic picture regarding current. So basically what's happening with electrons when we're talking about current. And to read more about this, you should see, this is in section 25.8, so C 25.8. And this is a little bit of a dry topic, so we haven't, it's not, it doesn't work very well to talk about it in class, but this is relevant for some homework problems. It's also relevant for stuff that we're going to see later with regards to the Hall effect and magnetism. So it's a good thing for you to have a resource on, and that's why I'm putting this together. So um, let me try and motivate this uh, in terms of what we've already talked about. So we've talked about the macroscopic picture. So, and what I mean by this is basically Ohm's law. Okay. Current, voltage, resistance, but none of this is at the level of what's going on with like an individual electron. And, and this is kind of our cartoon system of like a single resistor and voltage and current going around like this. And this is kind of the familiar way that you've encountered this topic so far, but this has some limitations. This picture. So for one, one limitation with this, electrons are the actual charge carriers, and compared to this picture where the current is going around like that, in actuality, electrons actually go in the opposite direction, which is kind of confusing because they're negatively charged. They flow in the opposite direction. If we're trying to have kind of a physical picture of like what's actually moving. And then another thing, another limitation with this so far is, or kind of where what we've been talking about so far breaks down, is that we've emphasized the fact that inside of a conductor, that E is always 0. Well, that is only the case in electrostatics. So in other words, once you have current, this doesn't apply. This isn't true anymore. So when there's current, it's not true anymore. Okay. And so, in actuality, like if we were to look at a piece of wire, and you imagine there's some current that's flowing through the wire, there is an electric field that's inside the wire that's pushing the charges along. So the question is basically, how do we relate these macroscopic ideas to the microscopic world? Okay, so that's kind of why we're talking about this topic. So let's flesh this out a little bit. And the kind of questions that we would get into, things come up like, how fast are the electrons going? And the quantity that we're going to get into is something called the drift velocity. So it's kind of the average speed along the wire, and that's called the drift velocity. So we'll look at an example on this topic in a second. But first, let's rewrite Ohm's law in terms of some properties. Um, so what does this look like? We start from our familiar expression, and let's recall a couple things. So we can remember that if we're talking about voltage, and so imagine we have now a piece of wire. Uh, you can express the voltage in terms of the electric field. So if you have a constant electric field, imagine you've applied a voltage, say, on a chunk of wire. There would be an electric field in the wire, and the wire has some length L. And so we could rewrite V as the integral of D, and in this kind of situation, it's just going to be the length of the wire times the electric field. And then we can also introduce a new piece of information, or a new definition, and that's something called the current density. So, and this is J, and J is defined as the current per cross-sectional area. So where this is a cross-section. So, imagine now your wire here has some area, cross-section. And so we can put those ingredients in here, and we already have a picture for the resistivity. So recall that the resistance is rho, the resistivity, times the length over the area. So if we put those ingredients together, we get basically E times length equals J times A times rho length over A. And notice, so some of these things are going to cancel out, and we're left with a pretty concise relationship between the electric field, the current density, and the resistivity. And we can also actually write this in terms of the conductivity as well, where the conductivity is just 1 over the resistivity. And so this is kind of the microscopic Ohm's law relationship. So this is the resistivity. This is conductivity. And so I know it's annoying when we use letters to mean different things. This is not the volume charge density and the surface charge density, respectively. This is the resistivity and conductivity. So ohm meters and 1 over ohm meters in this context. So that's the microscopic Ohm's law relationship. Next, let's look at the drift velocity in a little bit more detail. So this doesn't really tell you what's happening. This connection between E and rho and J doesn't tell you what's happening at a microscopic level, really. Doesn't explain what's happening to, say, an electron. So let's go into a little bit more detail. Let's derive an expression for the drift velocity. So derive the drift velocity. So kind of and I mentioned this before, this is sort of the average velocity along the wire. ED, it's kind of the average electron velocity along the wire. And kind of the picture here, imagine we have chunk of wire, and we talked before about there's an electric field that's in the wire, and the electrons are actually they're sort of bouncing around inside the wire, and on average they have some velocity, and that's the drift velocity. So when it's upstream of the electric field lines, because the electrons actually travel in the opposite direction, right? And so we can relate to current and what we already know. Vd to I and things we know. And we'll actually need a little bit of chemistry knowledge. So fundamentally, we know that current is charge, right? So let's think about this in terms of charge. And kind of the starting point is we're going to imagine the charge changing, basically. Change in charge. And it's going to depend on some ingredients here. So there's N. And what this is N is the number of free electrons per volume. And this is going to be a material property. Depends on, what kind of metal the wire is made out of, that kind of thing. We'll see that in a second with an example. It's also going to depend on sort of an effective volume that's changing. And it's going to depend on, and so where does that come from? We can visualize that by imagining our chunk of wire and think of it as like there's a section of length L where that length would be defined by the drift velocity in some amount of time. So think of it as like, that volume would correspond to the area times that length, the cross-sectional area times that. So V would be area times this Vd delta T. And then the last ingredient, the change in charge, well, it depends on, the charge per charge carrier. In this case, it's an electron. So you multiply those three things together, that's going to give you the change in charge. So what does that look like? Let's just put the pieces together. You get N, this volume, A, V drift, delta T, and then times the charge of the electron. Now, as we know, the current is defined as delta Q over delta T. So let's divide by that T on both sides. So this is just another way of saying the current is equal to N, the area, the drift velocity, charge of electron. Now, and then we can put this in terms of the thing that we just defined, the current density, by dividing out A. So J is I per A is going to be N Bd times the charge of the electron. And so this is kind of the thing that we're after here. We've derived an expression for the that contains the drift velocity in terms of the number of free charge carriers, little n, the charge of the electron, and the current density. So next, let's look at an example where we apply this. So, example. All right, so this example is in your text. So see example 25-14. And this will give us a chance to flesh out what we mean by number of charge carriers, etc. So the example is basically imagine a 3.2 millimeter diameter wire that's carrying 5 amps of current, and we want to find the current density and find the drift velocity. All right, so Let's do it. Current density is pretty straightforward. This is just I per cross-sectional area. So this is just going to be 5 amps divided by the cross-sectional area. So divide by pi r squared, where our r is going to be this 3.2 millimeters over 2. So, and if we plug those numbers in, we would find that this is 6.2 times 10 to the 5th amps per meter squared. So that's the current density. VD, what about the drift velocity? So the drift velocity, first, we're going to need little n. And this was the parameter that I mentioned before, the number of free electrons per volume. And we can get this really by referring back to some chemistry knowledge and looking at some dimensional analysis. So if you look up for copper, you can find the molar mass of copper, 63.5 grams per mole. And you can find its density of copper, density, rho d, let's call it. The density is 8.9 times 10 to the third kilograms per meter cubed. So ultimately what we're after is number of electrons per volume. So if we put these ingredients together, we can find this. So let's first think about the molar mass. You take, in 1 mole, there's 63.5 grams. So what's a mole? You know what a mole is in terms of Avogadro's number. Let's put that number over here also. Avogadro's number, this chemistry number that we have burned in the back of our brains, 6.02 times 10 to the 23rd. And it's just a number, right? So that means that there are 6.02 times 10 to the 23rd copper atoms per 63.5 grams. Okay. Let's just call this a number per mole. Good, so now we would have this this would be a number per gram. So then if we take advantage of the density, notice the density is mass per volume. So if we multiply this by the density, 8.9 times 10 to the third kilograms per meter cubed, notice we'll get rid of moles. So granted, we would have to convert from grams to kilograms, but we would get rid of factor of mass, and we would be left with a number per volume. And assuming that in copper there is 1 charge carrier per atom, then this would give you the number of carriers per volume. So if you multiply these ingredients together, you would find that N, or what does this give you? This gives you 8.4 times 10 to the 28th per meter cubed. So, and like I said, this is assuming, 1 electron per Cu atom. So basically what we've done is we've taken information about the density, the molar mass, Avogadro's number, you put that together and you can come up with the number per volume, which is what we need in order to compute the drift velocity. So next, let's use this number and put together what we know. We know that, like we defined up above, the current density is the drift velocity times n times the charge of the electron. So that would mean then that the drift velocity itself is just going to be the current density over n times the charge of the electron. And I'm just using the magnitude of the charge of the electron. And so if we put those ingredients together, we just computed the charge density. And we just computed n, number of free electrons per volume. And the charge of the electron, we know that number. Now notice, what is an amp but a coulomb per second? So coulombs and coulombs will cancel. Meters squared and meters squared will cancel, and we'll be left with a number that has units of meters per second of velocity, like we expect. And if we put these numbers together, what do we find? This gives us 4.6 times 10 to the negative 5 meters per second. So, in other words, this is like 0.05 millimeters per second. VD is very slow. So this is interesting. The speed of the electrons along the wire is actually very, very slow. It's 1/20th of a millimeter per second, which is crazy compared to how you know how fast electrical signals travel. They travel really fast, right? There's not a delay between when you turn a light switch on and when the light turns on due to the traveling of that signal. So the signal actually propagates much faster than the electrons themselves as they move through the wire, which is interesting. And this is this idea of drift velocity. And this is an idea that will come up again later when we get into some magnetism-related topics. So this is why we wanted to talk about this now and look at an example in detail now.